Okay, so in the last video, I went through, given the velocity of an object, how could we find the distance that it traveled? And we saw that the way to do that was we had to try to find the area beneath the graph of the velocity function. And so this leads us to the fundamental concept of integral calculus, which is the definite integral. So let's suppose f of x is a continuous function, and a and b are real numbers. So these are just some constants. So we define the definite integral from a to b, and this is denoted by the notation integral from a to b f of x dx, and this is the area, we define this by the area between the graph of f of x and the x-axis. So you may notice here that the notation we used for the definite integral looks a lot like the notation we used for the antiderivative several lectures ago. For the moment, I'd like you to pretend that you did not notice that. There's actually a very good reason why the notations look quite similar, which we're going to be getting to in a few lectures. But really, fundamentally, the antiderivative and the definite integral are very different concepts. And so I'd like you to distinguish this as a different object than the antiderivative. And it just represents the area beneath the curve of some graph of a function. So what does this look like? We have some points a and b on the x-axis. We have some function f of x. And the area between f of x and the x-axis is what we call the definite integral of this function between a and b. It's just how much area is beneath here. Now, there's a slight complication. What if we have a function which does something like this? Well, in this case, when the function is below the x-axis, this counts as negative area. So in this case, it looks like there's more area underneath the graph than above it. So the definite integral would actually give a negative value because we count this area as negative. Okay, so let's see some examples of how the definite integral works. So suppose we want to find the integral from 0 to 1 of square root 1 minus x squared dx. Well, let's draw a graph of this function. It looks something like this, and you've seen this before because this is what happens if you try to solve for the equation of a circle for y. So this is a quarter circle in the first quadrant of radius 1. So the area of a quarter circle is going to be equal to 1/4 pi r squared, which is equal to 1/4. And since this is the value of the area here, that means that this integral is just equal to 1/4. Let's do another example. Let's suppose I have a function which is a piecewise linear function So it goes down like this, then it's constant for a while, then it comes back up. Let's say that this height here is 5. This height down here is -3. This point will be 2. This point will be 3. This point will be 4. This point will be 5. So if we want to find the integral from, let's make this 6, the integral from 0 to 6 of this function f of x dx, well, we have to find the area beneath this curve, remembering that this area in here will count as negative. So this area in black will be positive. The area in red will be negative. So how can we estimate this? We first find the area of this triangle here. So the area of a triangle is 1/2 base times height. So we have the base has a length of 2, the height is 5. So we have 1/2 times 5 times 2. Then we have to subtract the area of this trapezoid. How can we do that? Well, we can break this up into 3 pieces. We've got these 2 triangles, which each give an area of 1/2 base times height. But since the triangles have the same dimensions, there's 2 of them, that means the 1/2 will go away. We just have base times height. The base is 1, the height is 3. So we have 1 times 3, and a minus sign because it's area below the x-axis. Then we also have the area of this rectangle here, which is 1 times 3 again. So we get minus that. Then lastly, we have the area of this triangle over here, which is another 1/2 times 5 times 2. If you add this all up, let's see, this gives you 10 minus 6, it looks like, which is equal to 4. So this is, hold on, my mistake. The base here was only 1, not 2. So we would only get, let's see, instead of 10, we'd have that minus 2.5, I guess. This is 7.5, and then this is only 1.5. Okay, so the point of these 2 examples is that if we have a nice geometric shape, like lines or semicircle or something that we're familiar with geometrically, then we can find the area and therefore find the definite integral just by using fundamental facts of geometry. But what if we have some complicated shape? Like, what if I have a function like this, and I want to find the integral from a to b? Well, this area is pretty complicated looking, and because the top of this graph is a strange shape, it's not a familiar shape that I know a formula for the area of. So we need to do something else to calculate this area. And it's such a strange shape. And so instead of trying to calculate the area of this shape directly, what we do is we try to estimate the area of the shape by replacing it with some shapes that are easy to calculate the area of. Well, the easiest thing to calculate area of is a rectangle. So let's replace this area by a bunch of rectangles. If I find the area of all these rectangles, it's not going to be exactly the area that I want because there's some stuff that's either getting left out. Over on the right here, there's some area that's getting left out. And on the left, there's some area that's being included that I really didn't want. So that means that I can find the area of all these rectangles easily enough. but it's not going to actually give me the area that I want. But it's just an approximation to the area. If I want a better approximation, then what I could do is use even more rectangles. And so now there's still, probably it can't be seen on the screen here, but there's still little bits of red area, which is either being not included when we wanted it or is being included when we didn't want it. But notice that the size of these red areas has shrunk a lot when we used more rectangles. And the idea of calculating these definite integrals is that we'd like to approximate the definite integral by a sum of some rectangles, and then let the number of rectangles tend to infinity, and that will give us the exact value of the area beneath the curve. So how does this work? We start off, let me draw a big picture here. We have some function. We have our point A, we have our point B. The first thing we want to do is decide how big are our rectangles going to be. So let's divide this region into n rectangles for some number n. And so what's the width of each of these rectangles? Well, it's going to be the total distance, b minus a, divided by the number of rectangles that we want. And we're going to call this distance delta x. So delta x is just this width here. So now, when we count off by delta x, we get a bunch of points in between a and b. And these are going to serve as the endpoints of our rectangles. So it would be nice to have some name for all these points. And I'm going to call them x1, x2, x3, x4, and so on, all the way up to eventually b will be xn, where n is the number of rectangles, and we could also call a x sub 0. So it would be nice to know what are the actual coordinates of these points, and it's fairly easy to calculate because x sub k, so in other words the kth point as we start counting over, is just going to be we start from whatever the x coordinate of a is, then we add delta x, so we add this distance here k times. So for example, x1 is just going to be a plus delta x. Then how do we get to x2? We add another delta x, that means it's a plus 2 delta x. x3 is a plus 3 delta x, and so on. So we have all these points, and so that means that the base of each rectangle will be from xk to xk plus 1. So in other words, for example, we'll get a rectangle between x2 and x3, between x3 and x4, and so on. Now these rectangles, we now know the dimensions of the base. The question is, what is the dimension of their height going to be? Well, we want it to somehow have something to do with the actual height of the function, so we get an estimate of the area under the curve. There's a couple choices that we could make. One is that we could take the left-hand endpoint of that interval. So we could take f of xk. This would give us the left endpoint. Or we could take f of xk plus 1 if we want to use the right endpoint. So if we use the left endpoint, then I'll get rectangles which look like this, right? So the height of the rectangle is the function value at the left side of the interval. If I redraw this graph over here, if I want to use the right endpoints, then my rectangles would look something like this. Both of these things will give me perfectly valid estimates for the area beneath this curve. Okay, this should be like that. Okay, so we draw all these rectangles, and then we want to find their areas. And then we add up the areas of all the rectangles to estimate the total area which is beneath the curve. So what's the area of a rectangle? Well, the area is going to be the distance of the base, which, remember, the width of each rectangle is delta x. Then we have to multiply by the height of the rectangle. So if we use the left-hand sum, the height of the first rectangle will be f of x0, right? So the height at this point. Then that just gives me the area of this first rectangle. I also want to add up the area of the second rectangle, so that gives me delta x, f of x1, plus delta x, f of x2, that's the area of the third rectangle. I continue adding up the areas all the way up to f of xn minus 1. That would be the area of this last rectangle here. And so notice I can factor out a delta x. And then if you recall your sigma notation, this can be written in a compact form as delta x sum from 1 up to n minus 1 f of x sub k. So this sigma 1 to n minus 1 f of xk just means plug in all the numbers between 1 and n minus 1 for the k here and add them all up, and that's why it's equivalent to this expression up here. So this is the left-hand sum. We can also approximate the area with the right-hand sum. The only difference is that now our first rectangle, the function height starts with x1 instead of x0, and instead of ending on n minus 1, it goes up to n. So that means that by a similar procedure, we can find the right-hand sum is going to look like this. Sorry, this one started at 0 up to n minus 1. So we get two approximations for the area. They're both perfectly valid. And if we took larger values of n, we get better approximations of the area. If we want to get the exact value, a, of the definite integral of this function, then what we would do is add up all these rectangles. And so we would take the limit of this sum as n goes to infinity. And it doesn't matter if we use the left-hand sum or the right-hand sum. They will both give us the same limit in the end, because both of them are approximating the same area beneath this graph. So this thing here gives us some indication of why we use the notation that we do for the definite integral. So the f of xk becomes the f of x here. That's what's known as the integrand. The delta x becomes the dx here. That represents a small change in x. And then the integral looks sort of like an elongated s. S stands for sum, which is coming from the sigma here. And then a and b are the limits of integration, so the range that we're going over. So sometimes when we have a sum like this, we call it a Riemann sum, and we give the same name to this sum. So basically a Riemann sum is just a sum of a bunch of areas of rectangles that approximates the area beneath the curve. And we call this thing here, the function, the integrand. So that's just some terminology associated with definite integrals. So great, we now have a way to calculate the definite integral. We take a Riemann sum, so we add up the areas of a bunch of rectangles. We let those rectangles get smaller and smaller, and as a result we get even more rectangles. And as we let the number of rectangles tend to infinity, we take this limit, and that's the area. One small problem. How on earth do we find the limit as n goes to infinity of this thing here? The answer to that question is not so easy. For example, if I pick a relatively simple function like f of x equals x squared, it could be done using, we could write down a formula for the sum of x squared, and then we could take a limit as n goes to infinity of that formula. But it is really fairly unpleasant, I would say, to do that. And if I give you something more complicated than x squared, like let's say, I don't know, the sum of x times e to the x, then suddenly calculating this sum becomes extremely difficult. Calculating the limit of the sum is also therefore extremely difficult. So we've done all this work and we've found an alternative way of calculating the area underneath the curve, but all we've done is sort of arrive at a new problem, which is how do we find this value? And so the bottom line is that while it's important to understand where this comes from and how it gives us the area underneath the curve, we still don't actually know how to calculate this thing. So we still have more work that we need to do, and that's going to be done in future lectures.